Hi everyone. In this video, I'm going to explain why we actually call it the adjoint state method and the adjoint equation. This is our Lagrangian. We implicitly constrain our PDE, R of UM, and phi is our misfit function. Typically, R of UM can be written as A sub M of U minus F sub M. In other words, that the strong form of the PDE is some A sub M, and this is usually a differential operator, such as divergence of M del U is what we had in the previous video, equals some forcing function F. And typically this will be independent of M unless you're actually inverting for this source term, in which case F sub M is M. But in general, it can depend on M. This is all I'm saying there. So let's derive the adjoint equation, considering the case when A sub M of U is linear. And when it is linear, we actually get an adjoint. And that is why it is called the adjoint state equation, or adjoint state method and the adjoint equation. So the adjoint equation is when we take partial with respect to U, partial phi, partial U, acting in the U hat direction, plus 0, because this term F sub M does not depend on U. And so let's just use the definition here. Limit as epsilon goes to 0 of dd epsilon, the inner product of A sub M of U plus epsilon U hat dotted into P. This is equal to partial phi, partial U, U hat, plus and now I'm invoking linearity with respect to U. So I can just split that apart. Now, this is of the form alpha plus epsilon beta, and we're taking the derivative of this, because this is just a number, and this is just a number. So its derivative is just beta. In other words, it is just this inner product. And the next step is where we introduce the adjoint. So this is A sub M of U hat acting in the P direction. And this is partial Lagrangian with respect to U, U hat. Now, if I want to actually compute the Frechet derivative of this, in other words, I want to abstract out this. So we've computed the Gateau derivative in the direction U hat, but if I want the Frechet derivative, and the adjoint equation is we're setting this to be 0 for a stationary condition. I have to vary U hat over all possible cases, but in this case, I'm not taking a dot product with respect to U hat, I'm taking it with respect to P. And so the adjoint is precisely that operator if you recall the definition of adjoint. If you recall the definition of adjoint, it is simply that operation. It is the operator such that whenever I do something on P in this other space, possibly other space, I can take the inner product of U hat with that adjoint. And so we can rewrite this as basically the integral of phi with respect to U AM star P U hat dx, if we're viewing these as actually having functions, LP type functions, equals partial Lagrangian partial U hat equals 0 for all U hat. That implies that the partial of the Lagrangian with respect to u is equal to partial phi, partial u, is 0, pointwise, or pointwise almost everywhere, where again we're assuming that this has an LP representation, and that is why we get the adjoint. In the next video, we will go through another example of this full framework and how we'll go about solving. We'll sort of tie the next, past 8 or 9 videos together to solve an inverse problem. And in case this was a bit quick, I'll give you guys an example where this adjoint is here, and you'll see how this process of going from here to here is done. Thank you guys for watching, and hope to see you in the next video.